Hello subscribers, hello those people who are following this course. We are starting now the lesson number 6, pressure losses at strike pipe and fittings. In this today's lesson, we will analyze how the pressure losses can be calculated for strike pipe, for valves, and for pipe fittings. Fittings, I mean, such as elbows or T's and valves, butterfly valves, row valves, gate valves, etc. So let's start with the lesson. The first, energy losses for strike pipes. Let's analyze first the strike pipes. The formula for calculation of this is the one that you are seeing on your screen. HL is equal to F multiplied by the length divided by diameter multiplied by the kinetic energy we have seen already before, expressed as energy per unit of weight. I mean the square velocity divided by 2 multiplied by acceleration due to gravity. F is the friction factor, L is the strike pipe length, D is the pipe diameter, the flow velocity, and the acceleration due to gravity. Since HL is equal to the differential pressure divided by density multiplied by gravity, we know these equations from previous lessons, we have seen before in previous lessons. We can replace this equation in the equation 1 and rearranging the equation, we obtain the equation to determine directly the pressure losses based on the friction factor for a strike pipe. The friction factor F will be estimated by using the Moody chart for pipe friction. Why estimated? Well, the friction factor will be estimated the same as pressure losses or head losses, because we do not calculate this, we simply estimate, but it is sufficient to estimate this. We will see when going beyond this point. This is the Moody chart. Let's analyze what we have in the chart axis. In the left vertical axis, we have the friction factor F. To the right, we have in the right vertical axis, we have the relative roughness. I mean the absolute roughness, epsilon divided by diameter d. And in the horizontal axis, we have the Reynolds number RE, that is equal to velocity multiplied by diameter divided by kinematic viscosity, or the relation between inertial forces and the viscous forces. But we have inside the graphic, we have this small table on the left bottom corner with materials. For some material we can see here, like concrete, glass, plastic, tubing, iron, steel. To the right, we have the absolute roughness in millimeters. Let's analyze what we have inside the graphic. To the left, we can see this line in rose color, this straight line. This is the zone of laminar flow. The laminar flow ends at a value of Reynolds of approximately 2000. The equation we see for laminar flow there written is F is equal to 64 divided by the Reynolds number. This is the Poisson equation. As you can see, for the laminar flow zone represented by this line I mentioned before, this straight line, the value of the friction factor does not depend on the value of the relative roughness, but only on Reynolds number. In this, let's go a little bit to the right. we can see this area colored in rose. This is the transition zone between the laminar and the turbulent flow. And to the right, we see several curves in rose color also, showing the value of the friction factor for different values of relative roughness. Let's pay attention to the dashed line that crosses all these curves. To the left of the dashed line, we have a curve, so the value of the friction factor changes with the Reynolds number and also with the relative roughness. To the right of this line, of the dashed line, we see a straight line, meaning that the friction factor only changes with the relative roughness, does not depend on the Reynolds number. Most of the real flows we will encounter in our practice will be located in general in the zone of complete turbulence. Let's determine the friction factor for a Reynolds number of, for example, 10 to the 5th power and a relative roughness of 0.006. To match the relative roughness value of 0.006, then move to the left to obtain the friction factor that is equal to 0.032. Well, let's move to the fittings and valves. How to calculate the energy losses, the pressure losses, the head losses at fitting accessories or valves. The formula we should use is this, where K is the resistance coefficient. We have to multiply this resistance coefficient that is different for every accessory, for every elbow, for every chi, or for every valve. A butterfly valve or a globe valve will have different, or a gate valve will have different value of this K resistance coefficient, and multiply this for the kinetic energy expressed as energy per unit of weight. If we want to calculate the same but in terms of differential pressure, is the same, to multiply K, but the kinetic energy expressed as energy per unit of volume. I mean in unit of pressure. Rho multiplied by square velocity divided by 2. The value of K can be selected, for example, from this document or books that I mentioned here, flow of fluids through valves fitting on pipes. This is the most known, the most famous crane. Also very popular that many people use is Cameron hydraulic data, FlowSetter from FlowSetter. And another, I think that is also good to keep in mind and to use for this is centrifugal pump handbook of Sorcerer. The value of this resistance coefficient K will be different between manufacturers. So it is important to understand, as I mentioned before, that we are in reality estimating the loss. We are not calculating the losses. For example, we have here in this table different values of K of the resistance coefficient for gate valve. See that the values are different depending on the position of the valve. It is, for example, if fully open, the value of K will be 0.17 for the gate valve, and if it is a quarter open, it will be 24, the value of K. Normally the gate valves should work fully open. This is a type of shut-off valve and not a regulation valve. For the plug disc, we have the same for the different position of the valve. For the butterfly valve, we have, depending on the degree of opening of this valve, different values of the coefficient K. This is a control valve sometimes, especially the triple centric butterfly valves. And below we have elbows, T's, bend, etc., etc. And to the right we have the equation where we have to replace or to include the value of K to obtain the pressure head losses, or the head losses, sorry, or the differential pressure loss. We have here a pipe connecting to two vessels. The fluid is moving from the left to the right. The pipe has a velocity, a diameter, and a length too. We have here the first fitting. It is the discharge of the tank, the entrance of the fluid from the tank to the pipe. And in the other tank, we have the discharge of the pipe to the tank. Applying what's seen before, what we obtain is HL is equal to the pressure loss caused by the first fitting, that is the discharge from the tank, K1 multiplied by kinetic energy at this point, plus the losses in the strike pipe, the friction factor by L, the length of the pipe, diameter of the pipe, by the kinetic energy at the pipe 2, plus the losses at accessory 3. In this case, we have that velocity is the same at every one of these accessories of pipe. So we can simplify the equation, and it's important to see the equation in this way that I'm showing now, as HL is equal to the sum of the resistance coefficients K1 and K3 plus F multiplied by L2 divided by G2 multiplied by kinetic energy. There is another concept. I prefer personally to use this, but many people and many calculation programs use the concept of K, of resistance coefficient, instead of the equivalent length. Since I do not use this very frequently, I prefer to use this. For me, it's more funny. Here we have the equation we mentioned before to calculate the pressure or the head losses for a strike pipe and the head losses for a fitting or a valve. Then in equation C, as we see, we can say that the value of K, the resistance coefficient, is equal to the friction factor multiplied by an equivalent length divided by D. The parameter L equivalent is the equivalent length of strike pipe corresponding to the accessory that we are analyzing. We are transforming our elbow in an equivalent length of strike pipe. It is, for me, very interesting, and as I mentioned before, this is the method I use always because it seems to me very, very, very funny. We can find the value of L equivalent in two forms, in handbooks or manuals. As indicated in equation 7, as the relationship between the equivalent length and diameter, or directly as an equivalent length. In this diagram, we can see the value of the equivalent length of strike pipe for different valves and accessories or fittings. We can see here a globe valve, an angle valve, a swing check valve, and many other fittings such as elbows, ticks, southern enlargement. At the center, we see the equivalent length of strike pipe. In this line, we have this scale with these values. And to the right, the last line is the diameter of the pipe, or sorry, of the accessory or of the bulb. Let's suppose we would like to determine the equivalent length of with the diameter of 42 inches. If we join the line of the bulb with the line of the diameter, we obtain that the value of the equivalent length is approximately 1,200 feet. This is the way in which we can use this diagram. The explanation is, you can see the explanation here above the graphic. Let's do the same here for the situation or the sketch we have before with the pipe connecting the two tanks. But now, instead of the resistance coefficients, we have the equivalent length accessory 1. The same at the accessory 3. We have an equivalent or length of this accessory. So the equation now remains the following way. HL is equal to the head losses of the accessory 1, but now what we use is the friction factor by the ratio of the equivalent length 1 divided by the diameter at this point 1, velocity or kinetic energy multiplied by kinetic energy at this point, plus the friction factor multiplied by the length of the pipe and divided by diameter multiplied by kinetic energy on the pipe, plus the last one or the last accessory 3, where we have the friction factor multiplied by the corresponding equivalent length of this accessory divided by diameter and multiplied by velocity. In this case, velocity and diameters are the same. So we can simplify the equation. It's good to see the equation in this way, although not always we can do this, but the practical meaning of this method is what I want to show you now. As you can see, the value of the head losses can be determined at or are equal to the friction factor multiplied by the total length, including the equivalent length of the accessories. I mean the sum of L equivalent 1 plus the stripe pipe length plus L equivalent 3 divided by diameter and multiplied by kinetic energy. So this is the end of this lesson. I will be waiting for you in the next lesson. Bye bye.